Hello there, welcome back to our channel, and this time we have brought to you a special circuit using transistors, and this circuit is called as free running oscillator. It is also called as multivibrator. So there are three types of multivibrator. One is astable, second is monostable, and third is bistable. So out of these three types, we are going to see the operation principle of the first one, that is astable. So it has two quasi-stable states, that is on and off, and it is a free running multivibrator. So it's basically an oscillator. And what you can see, we are using a transistors, two identical transistor Q1 and Q2. These transistors are of the type 2 and 3904. So let me right click on this transistor and show you the properties of this transistor. So here is a spice model for the transistor. This is the part number, manufacturer name. It is an NPN transistor. The maximum rating across the collector and emitter voltage, open circuit voltage, is 40 volt. The maximum current it can withstand from collector to emitter is 200 milliampere. It is a spice model dot model 2 and 3904, and it is NPN, and we are interested in having the beta factor of 300 actually. So, okay, and the rest of the parameters we have explained in several of our earlier modules. So refer to that if you are new. So what you see here, this is a perfectly symmetric circuit. From the middle of the part, we see the left side and the right side is perfectly symmetry. We have two transistors, we have two capacitors, we have two resistors, and there are two load resistors also. So because it is an oscillator, it will use a positive feedback in the loop, and therefore it will start producing an oscillation waveform. It could be a square wave, it could be a rectangular wave, it could be a pulse, and this kind of multivibrator circuits are used for a delay, to produce the delay in the circuitries. Okay, when you read delay and all those things. So we continue explaining this, the working behavior of this explain. So, so from the transistor Q1, we have the load resistance R2, and then from the collector pin of the transistor, we take a kind of resistor. We use the negative feedback and give it to the base through resistor R4. So it's basically a common emitter circuit, common emitter amplifier. And there is this R4 that is used to bias this transistor also. So R4 has two purposes: to provide the negative feedback from collector to the base, and to provide the bias and set the operating point of this transistor Q1. Now for the transistor Q2, we have a load resistance R1 and Q2. This transistor circuit is also a common emitter amplifier. It uses collector to base biasing scheme using resistor R3. At the same time, R3 is providing a negative feedback from collector to emitter. So since it is an common emitter amplifier and it is an inverting amplifier, so it will provide us 180-degree phase shift output, and this amplifier is also going to provide 180-degree phase shift output. So total combination of the circuit in this loop is going to provide a 180-degree plus 180-degree, that is 360-degree phase shift or 0-degree phase shift, which is one of the essential criteria to sustain an oscillation. Okay. And what you are saying, that the output of the collector Q1 is becoming an input to the base of Q2 through this capacitor C1, and the output of Q2 is becoming an input of the transistor Q1 through this capacitor C2. So both the capacitors have been chosen the equal values of 0.1 microfarad, 0.1 microfarad, The resistor R3 and R4 are approximately of the same values, that is 101K and 100K. There is a slight difference between the two values of the resistors. You have to write in the comment why is that different so? Why are not they exactly equal? And what if we make them equal? And then similarly, R1 and R2, which are the load resistance for Q1 and Q2, are also of the same value. We are using a 5-volt DC power supply. It is an oscillator circuit, and therefore we don't have or don't require an external input signal to the circuit, such as one we use for an amplifier. This is an oscillator. So it is a time generation circuit, time waveform generation circuit, and it doesn't require any external input except the DC power supply. So what happens is that, like I said, there is no fixed operating point to this circuit. Once the power supply is switched on, one of the transistor is in on state while second transistor is in off state. This condition charges one of the capacitor to the full value of VCC, or the DC power supply. And then as the voltage on the one of the capacitor rises, it becomes the charging voltage or turn on voltage for the second transistor, which is in the off condition initially. Then the second transistor turns on and the first transistor turns off, and the cycle continues. And therefore, we have the unstable state. That's why we call it as a quasi-stable states, and or quasi means semi-stable states. And therefore, transistor Q1 and Q2 switches periodically, and on time and off time. On time or the off time of the transistors are determined by the values of C1, C2, R3, and R4. And that turn on time plus turn off time is total time, and reciprocal of the total time gives you the switching frequency of this circuit. So when you are using the 5-volt DC power supply, and as I said, I just explained you the working principle of this circuit. So we are running transient analysis for this circuit. For example, we are running this analysis dot run. We will run the simulations for 25 milliseconds, and there is a command startup. So it is an oscillator circuit. That's why it will start building up the waveform. And this is the startup time that we are giving it. So let us simulate this circuit. So what I'll do, I will click simulate and I will click run. And now the waveform has appeared. I can click at this node, which is the output of first state, and at this node, I will have another output. So both will be in phase shifted to each other. So let me click it here. Look at this, the voltage at this node, that is collector of transistor Q1. I have this pulse waveform that is coming here. There is a little bit distortion here, but still it is catching up the oscillation at about 6 milliseconds. And then I have this pulse waveform that is steadily oscillating between this one, right? So on time and off time of this can be measured. You can actually put some a cursor here and measure the on time and off time. Now let me click here. You can see that the blue is the node voltage at this, and both these waveforms are a 180-degree phase shift to each other. So that's how these states, the transistor Q1 and Q2, are oscillating one after the another. What if I want to change the capacitance little bit, let's say 0.02 micron. And if I do such change, I simulate the waveform, and then you can see the time period for the voltage at the collector of the Q2, that is the blue line, that time period has increased. while the time period for the Q1 is going to be the same. Okay, so this is how you can do that. But now you will not have uh, stable states, because the one state having a different frequency and another state is having the different frequency. Okay, so that's how you can play around with changing the values and then simulate your circuit. So hope you understood this circuit behavior, and once you understand, put some comment, like it, share it, subscribe it, and stay tuned for more informative videos like this. Next time, we will bring to you some other circuits or some other variations into the circuit. Let me show you also some variations into the circuit. Okay. So let me show you improved version or another version of this as of the first circuit, that is an astable multivibrator. So here is the improved version or another version. So look at the difference between the circuit in the left side and the right side. So you have the same capacitor and the resistor. However, these resistors, which are arranged in this fashion, I have taken up, and through the capacitors, I have again provided the base inputs to both the transistors. So there is a slight modification from into the left side of the circuit, and the right side of the circuit is presented. So let us now simulate this. And after simulation, you can now see the waveforms for the first part, both the sides. And now this is we have seen. Now I will right click, add plot pane, and look at the waveforms for the right side circuit. So I click here and I have a smooth square waveform generation, and I have the collector of the Q4 also is the smooth generation. So the second part of the circuit looks better, and that's how you can actually see the modification of it. So go for the second side of the circuit. Okay, so again, if you just want to play around with the changing the time period and the frequency therefore of the waveform, just play with the capacitors. So hope you like this circuit, and you enjoyed this video, and like and subscribe, comment, put some comment, share it for with others for a wider reach, and stay tuned. Till then, wish you happy learning.